Let me introduce myself. My name is Chris Berger. I'm a technologist at Intel leading a new team that has really a very singular and laser-focused mission on one thing. Intel, for the last couple of years, has been developing a new set of composable technologies that we call rack-scale design. And the mission of my team is to make the adoption of this new set of composable technologies a success. Very simple. So what I'd like to talk to you about today is really how we can re-architect the data center for growth. And there's three words here, and when I talk about advancing data center for agility and scale, it's really three words here that are important. One is, how do you get from A to B? Right? As Intel, clearly we have a very strong opinion and some thoughts on what it takes to advance data centers over the next couple of years. Do that in an agile way and also do it at scale. So I want to start this presentation by talking first about two hypertrends that I don't think are going to be very controversial. I can figure out how this, oh, there we go. And then really take you through some of the key concepts and technologies, but also some end-user case studies that have developed these technologies in practice, and then give you a little bit of a roadmap, additional roadmap on how we believe composable architectures are going to evolve. Ethan, who's then presenting after me, is actually going to show you the Wiwynn instantiation of that technology. So this is all how it fits together. So let's start with kind of the big picture stuff. Clearly there's, and you've seen this probably a million times already, there's kind of 5 key pillars to the evolution of the data center industry today. There's lots more connected devices, right? Everybody has his famous numbers or favorite numbers of 50 billion, 100 billion by 2025. It really doesn't matter, but there's going to be lots of more connected devices. There's a strong move towards cloud computing. That's now a reality. The transformation of the network that Bill was talking about when he introduced ONF is happening now. Personally, I've been very much engaged in actually creating that momentum behind software-defined networking and network functions virtualization. That is absolutely now being deployed in a number of operator networks, as well as cloud service providers and enterprises. There's an undeniable growth of AI and analytics that is happening now in data centers that deliver solutions for autonomous driving, or even something as relatively straightforward and as simple kind of car sharing services. All of that is creating this deluge of data that's driving change. And the change is both on the business side as well as on the technology side. So I don't think there's much, there's a big controversy around that. The second thing is now we're getting a little bit more controversial is, so what does this mean, right? So traditionally when you looked at a compute node or a compute resource, you really just focus on what it can do for compute. Now, compute resources can do networking, right? And we're seeing a tremendous growth that's driven by the network transformation, right? 1,000x, 100,000x of data traffic on an AT&T network that's happening. Artificial intelligence, the introduction of that can drive 12x compute cycle increases. And also new things such as visual computing, especially if that is integrated with some of the new edge kind of technologies, is expected to tremendously increase the need for compute cycles. So these kind of two megatrends combined create a need for change. And it's actually difficult to articulate that change in a coherent way, but we tried. So let me show. Oh. There you go. So let me take you through that slide because there's a lot of it on here. And I'm glad that everybody is going to get a copy of it afterwards because it will probably take you 5 to 10 minutes to parse it. But let me talk you through some of the highlights here. What Intel has been doing and continues to do is articulate an opinion and a vision of how data center technologies is going to evolve. And we're doing that across a number of vectors, right? Going back to, say, the mid-90s, where we had highly complex systems that had significant upfront costs, to what we believe the future is going to look like, where the data center infrastructure needs to be much more service-oriented and focused on business cases that are really much more controlled and provided on a cost-per-use type of basis. And then on the other scale here, we have the aspects such as scalability and ability to customize your technology from being less scalable to being fully scalable. And new technologies and capabilities from telemetry influencing AI engines, for example, are really important here. So over time, you see the evolution of the data center. I don't think there's, again, much controversy here to blade servers, introduction of virtualization in 2008, 2009, VMware certainly driving very profitable business models there, to cloud computing, and now, and you can you look at this as a little bit of a range, where what we call the era of fog computing. And there's a couple of characteristics to that era, to that phase. First of all, we have much more of a move towards a software-defined, network-based, and distributed set of data centers. So I'm going to talk actually about that a little bit more when I explain the concepts of rack scale design. But also what Bill was talking about before was Cord and some of the projects that they've been doing in the ONF for owners, for example, and to develop SDN controllers. That really is another outcome of this kind of phase. The next characteristic of this phase is kind of having composability introduced also at the hardware level. And again, as we're talking about rack scale design, I'm going to give you some concrete examples, and then Ethan is going to show you what composability actually means in practice. And then I'm just going to pick one more on this. It's the use of infrastructure accelerators, right? And this agenda today is actually characteristic of that as well, right? We have a session on, hopefully, on GPU usage in data centers, but also from an Intel perspective, using FPGAs for workload acceleration is a key part and characteristic of that fog computing stage. Now, we also have a vision to progress from that. And the vision is what we call ambient computing. And that kind of goes into the 2020 type of technologies. And it doesn't mean that every part of this vision has to be executed within the 2020 plus type of timeframes. There are examples now that where service providers are already doing this today. But there are a couple of key words here that are important when talking about this vision. And the first key words that I want to see with you is zero touch, right? A fully autonomous data center infrastructure that can use, for example, telemetry data and make, in real time, decisions about workload placement, for example. The other key characteristics here, and I'm going to talk a little bit about this, is the usage of AI and robotics everywhere, right? So we've already seen, pictures of robots rolling through data centers, pulling out servers, putting in a new one, right? Using RFID-based tagging to keep track of all of that. So these kinds of, both physical hardware delivery systems as well as software delivery systems are just going to be another part and characteristic of this zero-touch, fully automated infrastructure. Again, I realize it's a little bit of an eye chart. We can probably spend a whole presentation just on explaining that. But I wanted to give you a little bit of a kind of a vision statement, use that opportunity on where Intel is seeing the industry evolve. Now, another vision slide. So one of the consequences of that vision that we would like to suggest here is that analytics as one of the defining items of an intelligent infrastructure also will have to evolve, and how analytics is implemented in a data center has to evolve. So first of all, we're kind of roughly, from an analytics perspective, for the majority of data center operators today, kind of in the second phase here, where we have a lot of diagnostic analytics happening, right, driving insight on what happened and why it happened. But in the future, we're really moving towards that phase towards cognitive analytics, where it's really emulating the human mind. And again, think about that with the context of moving towards zero-touch infrastructure, where we have kind of computerized human thought, simulation, and actions towards a fully autonomous enterprise or cloud service provider data center. And there's some interim steps here, predictive analytics, what will happen, when, and why. You see quite a bit of technology innovation coming out of Silicon Valley that is focused on that, as well as then prescriptive analytics that has more capabilities and more characteristics to actually recommend a course of action based on the data that is being seen. All right, so why does this matter? We think there's three things here that that really are the result of these kind of mega trends that are happening in the industry, and then this kind of maturity model that Intel believes is going to characterize the evolution of the data center. First of all, any new technology that is being promoted in the data center just has to be fast and easy to deploy. Right? That is one of the core characteristics. It's got to be deployable right away. You can't do an install cycle of weeks to actually get new resources up to speed. The growth of the industry does not allow you to do that anymore. The second point is around efficient resource management. Clearly, as Intel, we would love to sell you servers and Wiwynn as well with Intel processors in it, as many as you can take. But TCO is a reality in the industry. So managing your resources is just efficiently is one of the key characteristics that is really key to driving that hyperscale agility. And then the third point, and this is where I'm going to go into a little bit more detail and show you some use cases, is using composable infrastructure that we're talking about, and that's called rack scale design. So one of the things that Intel is very keen on communicating and is very committed to is that it's time to rethink the data center in a hyperscale age. Traditionally, the server is the unit of purchase, right? I'm not talking about TORs or kind of storage-based JBODs or JBODs right now, but traditionally, the server is the unit of purchase. And what we're suggesting is that in the future, the rack is the unit of purchase, but the rack is defined in a disaggregated hardware array and has software intelligence on top to manage these resources. So rather than having a server that has direct attached I/O for hard disks, for NIC cards, etc., really what we're talking about disaggregating the rack with a set of compute pools, storage drawers that can hold hard disks or SSDs, and then also having an accelerator drawer. And again, Wiwynn has a number of offers actually here that we can showcase to you. So this is one of the key points, right? The unit of purchase is changing. So let me go on a little bit more into details here. We talked about disintegration and composability. Again, I'm going to give you a little bit more detail on composability, but what we call at Intel, we call this optimizing your data center for the software-defined infrastructure. And there's, again, 3 points here that characterize it. One is, it's got to be based on standard APIs. And I'm going to talk about how we actually use Redfish and Swordfish as some of these key open source and open standard-based mechanisms to drive that interoperability goal and make it a reality. The second one is it has to be disaggregated and composable so that the APIs can use for efficiency. And then the third one is clearly every purchasing department will have multi-vendor support as a requirement. So there's got to be a broad ecosystem of vendors that can create solutions that can be mixed and matched. So within Intel, we call this, the Intel rack scale design, which is an open source, Apache licensed set of technologies that we're working on with companies such as Wiwynn. And there's really 3 goals that we're looking for with rack scale design. One is we can prove much higher workload performance and efficiency. The resources are pooled for greater utilization. I'm going to show you 3 case studies to go through that. And this is also important. Pooling allows for independent upgrade cycles. Before, when you had a distinct unique server, every time you wanted to do an upgrade, you had to take the entire server out and basically find a home for it, because it's now end of life. Whereas with pooling, if you want to have greater SSDs, or just swap out the compute pool, or move to the latest version of FPGAs from Intel, you just change that component only. So that's a measurable benefit. So let me give you some concrete examples for that. So the first example that I'm going to talk about is a company in the Czech Republic called SafetyX. So they're a standard cloud service provider. They're running the largest open stack in Central Europe. And one of the key problems that they had was, how can they optimize their PUE data, because it's a new data center, by using some of the advanced power and thermal telemetry data that Intel provides. So clearly, their PUE at the beginning was really terrible, and by using some of the telemetry results that we provided through the rack scale system, they were able to reduce it by 17%, or actually by a little bit more, because they could run their IOs a lot hotter, and then the OpEx costs went down by 70%. But that's, to me, just a kind of a temporary point-in-time type of benefit. What is really interesting now is using advanced telemetry for power and thermal to do workload-dependent cooling. Right? Typically, when you have your data center, you run your standard hot aisle or cold aisle, and the entire aisle needs to be cooled consistently. Now, with some of the telemetry that we have built into RSD, you can actually, per workload that you're running on the rack, you can influence your cooling, and therefore drive a much more dynamic investment and OpEx structure into your data center. Again, come to me and I'll talk to you a little bit more about that. Second concrete use case here. I'm not sure how many of you are really that familiar with maybe HPC high-performance computing workloads, but the workload that we're using here is from the Barcelona Supercomputer Center, and it's called SMUFFIN. It's basically mutation analysis, genome sequencing type of workload. It's a very typical workload if you want to find out whether a genome has a propensity to get cancer in the future. And one of the advantages of RSD-based systems is that you can pool resources. So traditionally in scenario one, you have a direct attach NVMe, and the utilization of that NVMe drive, as you can see against this workload, is relatively modest. Right? By changing the scenario to have NVMe over fabric pooling here, in this case, we actually just have one centralized NVMe target, so you don't need 2 additional NVMEs, even though as Intel, of course, we like to sell you as many NVMe drives and technology as possible, but in this case, you can actually optimize it, and in this instance, we accomplished almost the same performance within less than 5% of this high-performance computing workload against a single NVMe target. And that's really quite a concrete cost saving for that particular center and use case. Let me give you one more. GPU pooling and FPGA pooling is now one of the hottest trends in data centers, right? Because these represent one of the most expensive items that you have in your data center. So what we've done, the traditional configuration is that you have, again, direct attach platform acceleration cards, like from Intel, for example, from our Altera group, where you have one FPGA in every card, in every server. We've actually created a scenario where you can have one Xeon server have multiple FPGAs, so disaggregating the FPGA attachment, and therefore serving those 2 servers, additional 2 Xeon servers, that could be either not used at all or used for other purposes. But what we showed with this financial workload called Levi's is that we can actually create significantly better performance by clustering and pooling all of these FPGAs in one server and meet the SLA that this financial services organization had with significantly less hardware. And again, Ethan is actually will showcase you some of these NVMe clustering capabilities as well. Now let me give you a quick outlook to the future for composable infrastructure type of technologies. They're really characterized, or the roadmap is really characterized by 2 development trends. First, on resource pooling. So from an Intel perspective, it's just a very simple message here. Any Intel component that can be pooled will be pooled. And we're on a mission to enable that, right? So as Intel is bringing out AI-specific chipsets or machine learning specific chipsets, we are, over time, going to all offer them in a pooled scenario, because that's just a lot more efficient, it drives a lot more agility, and it drives a lot more scale. And then on the bottom side is open manageability. Here we're really focusing on some of the lower layer open standards APIs for Redfish and Swordfish, or then on the networking side, Yang to Redfish integration. But that also actually extends to a number of initiatives that we have in place right now to integrate these composable hardware infrastructures into OpenStack, Kubernetes, so that the experience for a network administrator is very similar to what they're used to with traditional legacy-based servers. So how can you get access to it and learn more? First of all, as Intel, of course, we have a dedicated website on that, on intel.com, called Intel RSD, where you can learn more, white papers, case studies, all of that information is already available. And then, for this context here with Wiwynn, Wiwynn actually built a great set of enabling technologies called the Wiwynn Cluster Manager that Ethan in his next presentation is going to talk about. All right, with that, should there be any questions, please feel free to come and talk to me. If not, we can move on to the next presentation or to lunch, I'm not sure.